So, what I discussed last couple of classes is about the necessary and sufficient condition for two mode Gaussian state to be entangled. Okay. And what we said is that so the can you see this part? So, this two mode state, two mode Gaussian state. So, a two mode Gaussian state rho a b is separable if and only if rho a b t b is greater than or equal to 0. That was what we have discussed, right. And we said that this is equivalent to some local symplectic invariant condition, which is what was that in terms of determinant of A. So, your this has the covariance matrix gamma. So, this gamma I have taken as A C transpose B. So, this is a 4 by 4 real matrix. What was the condition? Determinant of this times determinant of B, right. And then what was that minus, maybe let me look at the expression. Yes, okay. So, yeah, so not minus, this is plus 1 by 4 minus magnitude of determinant of C whole square minus trace of A j, C j, B j, C transpose j. This is greater than or equal to 1 by 4 determinant of A plus determinant of B, right. This is the condition. Okay. So, what we are going to discuss today is how to verify this condition using two mode I mean using lights of two mode system and mostly using linear optics. Okay. So, this is what we are going to discuss. Now, and this is based on the Simon's work, this is the necessary sufficient condition, but okay. So, this is what we are going to discuss now, how to verify this thing. Okay. Right. So, let me go to the next slide. Okay. Now, here we have a motivation for doing this, which is slightly more general than what has been discussed in Simon's paper. Okay. In the sense that of course, we know entanglement is very useful, all that things are known, is quite useful resource. But we need to also know whether whenever a source produces some entangled state, whether that is really entangled or not, because when the source produces entanglement, then it should be transmitted to far apart parties, and during this transmission some of the entanglement might get lost. Okay. So, we need to know whether whatever the shared state between the two parties far apart labs, whether that is entangled or not. Okay. Right. And we know for finite dimensional systems, if I know the entangled state, then there are ways to detect its entanglement using this entanglement witness and all that, but you need to know the state, you need to have information about the state. So, what we want here is we only want the information that the state 2 mode state is Gaussian, nothing more, nothing less we want. So, given that information, can we figure out whether the state is entangled or not? Okay. So, that is the question, and therefore, it boils down to detection of entanglement in 2 mode Gaussian state in a universal way, universal in the sense that you do not need to know what exactly the Gaussian state is. Okay. Now, why this is useful? Because for experimentalists this is always useful, right. For experimentalist, if you want the experimentalist to set up his or her lab depending upon the different choices of Gaussian state, it will be very difficult. So, this is what we are trying to do is a universal detection of entanglement in 2 mode Gaussian state. Okay. Right. Now, one more thing I must say, that unlike in the case of finite dimensional systems, where we know this Hahn-Banach theorem exists and all that things are there, although Hahn-Banach theorem will also work for infinite dimensional system, but to come up with an entanglement witness given an entangled state is difficult in the case of infinite dimensional system. Okay. And there is, as far as I know, there is no I would say algorithm for doing that. Discrete system, Hahn-Banach theorem does not provide you an algorithm, but still it is for example, if your state is NPT, of course, you can do that, and if you take the partial transposition of the state and then figure out an eigenstate of that partially transposed density matrix which corresponds to negative eigenvalue, then of course, this is entangled, no doubt, but this eigenstate corresponding to the negative eigenvalue, that has to be entangled, and that will help you to create an entanglement witness. Okay. For PPT entangled state, things are not so easy, you will have to go through these decomposable positive maps and all those things, but for NPT state it is relatively easy. For Gaussian state, I mean for infinite dimensional system, in principle you can do that, but still it is not so easy. Okay. In principle you can do. NPT of course work, but the point is that you will have to be bit careful about the convergence and all those things. Okay. So, as I said, we have to look for something which is universal. Okay. So, to overcome such this hurdle, because for each state you will have to design one experimental setup for doing that. So, overcome such hurdle, it is important to design entanglement detection scheme physically, not just mathematically, physically, which has a universal nature, in the sense that such a scheme can detect entanglement in a reasonably large class of states, even if it is not a full class of states, okay, for given bipartite or multipartite system. Right. So, this is basically the idea. Okay. So, here is the what I told you. So, let us say this is the source which produces this bipartite state locally, and then a particle A has been sent through some channel, B has been sent through some channel, and then they share this state rho prime. Of course, rho prime and rho are not same, this is a modified version, and what is it that you need to look at is to test whether this is entangled. Even if this is entangled, there is no guarantee that this will be entangled. Okay. So, okay. Now, we might say that why are you bothered about this universal detection of entanglement in 2 mode Gaussian state? What is so big deal about it? Okay. So, this fact is known. If I give you a 2 qubit state, okay, which is this rho AB, this is a 2 qubit, rho AB is a 2 qubit state, and if somebody supplies you 4 copies of this state. So, rho A B tensor 4, and this can be any 2 qubit state. I do not know what that state is, only thing I know is it is a 2 qubit state. Then you can always figure out a Hermitian operator W, which is independent of this rho A B. It has nothing to do with rho A B. It is a fixed Hermitian operator which acts on this composite system. So, on Alice's side 4 qubit system, on Bob's side 4 qubit system. So, this W as a Hermitian operator acts on this 16 cross 16 system, such that if I perform measurement of W on the 4 copies of the state, the average value of the measurement result will be same as determinant of partial transpose of the 2 qubit state. Okay. And this is true whatever your 2 qubit state rho A B. So, this one can always prove. I mean, in fact, there is a specific form of W. Maybe next time I will tell you how to get that form. Basically, it if you write down some matrix in the eigenvalue equation, then the coefficient will help us to figure out this form of W. And because this is a Hermitian operator acting on this, we know that this can be realized by performing measurement on Alice's side and measurement on Bob's side, and then classical communication. So, locally it can be realized. So, here you see that in order to figure out whether the state is in rho A B is entangled or not, you just perform measurement of this Hermitian operator on the 16 cross 16 system, that means 4 copies of the state, and that will tell you. And why this is important? Because signature of this determinant of partial transposition, if it is so, if this is negative, then we know for sure that rho A B is entangled. If it is non-negative, then we know for sure that rho A B is separable. So, this is equivalent to this Perez-Horodecky criteria for 2 qubit system. Okay. And this is the work which people have, this Gaussian and others, they have done in back in 2008. Okay. Right. So, this you can say is that this is universal detection of entanglement in 2 qubit state, and you can in principle also provide a measure of entanglement for this. For example, you can take magnitude of these and then connect it with some measure of entanglement in the 2 qubit state rho A B, that is also possible. Okay. But I am only considering detection of entanglement. For the time being, I am not so much interested in the in measuring the amount of entanglement. In principle, that can also be done. Okay. And you see that this has nothing to do with mathematical property, although partial transposition is a mathematical operation, but this is not mathematical, this is you can realize physically. Okay. In fact, later in 2015, this is Bartkevich and others, they provided a realization of this universal 2 qubit entanglement detection. That means, they provided a scheme of measuring these W in optical setup, I mean using these 2 photon polarized states. Okay. So, rho A B is a 2 photon polarized entangled state. So, that they have done, right. Okay. So, our motivation was basically this. So, okay, so I will come to that later. So, what we have done later is that we have extended this work of Gaussian, this work, to a situation where the measuring devices can have errors, like your detection, the photo detectors are erroneous and all that. So, even in that case, you can show that this scheme will work. Okay. So, we have extended this scheme for, so this is universal entanglement detection for 2 qubit state, and we have extended this scheme to measurement device independent scheme, in the sense that even if there are detection errors or inefficiencies, still this scheme will work. Okay. So, this is the work where we have done this thing. Yes. No bound. Well, if it is 100% inefficient, of course it will not work.
Like even 50%,
60%, 70%, nothing will, it will work. Okay.
the operator.
So, it will work means what? So, what is the philosophy behind it? So, philosophy is, when we talk about the measurement device independent scheme, is that no separable state should be detected as entangled. That is the philosophy. Entangled state may be detected as separable, that is possible, but no separable state should be detected as entangled.
Should not false positive should not.
Yes, 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 and that is very serious if we use these entangled states for this like QKD, that will be very serious case, right. So, this scheme will provide you a universal entanglement detection in 2 qubit states in a measurement device independent way. Okay. Right. Now, you might say that this is fine, this works for 2 qubits, why should it work for 2 mode Gaussian state? Okay. Why should this kind of scheme will work? Okay. So, what we had in mind that look at this for 2 qubit states, criteria for entanglement is that determinant of this partial transposition should be non-negative or negative. If it is non-negative, then this rho a b is separable. If it is negative, the determinant, then rho a b is entangled. Okay. So, that is, you can say yes or no condition. Okay. If you look at that criteria, this Simon's criteria, Perez-Hordecki criteria, it is same, right, at least it looks similar for Gaussian state. So, 2 mode Gaussian state is entangled or is separable if and only if you take partial transposition, this is positive semi definite. Okay. So, that was the motivation behind our work to figure out whether one can design such a universal detection scheme of entanglement. So, that was the idea. Okay. Of course, for 2 mode Gaussian state, we do not have a condition in terms of signature of this. We have condition like this, this local symplectic invariant form, but that is okay, that is fine, that makes life difficult. Yeah, so this is we have done, of course, but still more need to be done there. I will tell you what are the things we have done and what are the things we are still trying.
So, trying as in for the 2 qubit states itself or for the Gaussian?
For 2 mode Gaussian state, 2 qubit state people have done already.
So, this W is realizable by local operations.
I mean, on Alice's side, Alice will perform some set of measurement, Bob's side, Bob will perform some set of measurement, but on 4 qubits, not just, and then they can communicate classically.
It is proven to be LOCC or by construction it is LOCC?
By construction it is LOCC.
So, that W, the way they constructed it as
No. Any Hermitian operator for standard quantum mechanics, if it is on a bipartite system, in this case it is 16 cross 16 system, you can in principle realize it by LOCC, right? Any Hermitian operator. Because you can write in some basis, right, like in this case maybe some Gelman basis for Alice, some Gelman basis for Bob, and then you can just you will have to communicate what measure.
say global operations.
Global, of course you can do, but in our case we do not need to do, because these are far apart labs. So, you cannot. I am not talking about this locally, means Alice performs one operation and Bob performs one operation, not like that. Alice performs set of operation, Bob performs set of operation, but you will have to choose which from this set Alice performs which operation and Bob performs which operation. That choice has to be made by classical communication.
Yes, that is.
It is like Bell's theorem, Bell operator can be realized by local measurements, right. Classical communication there you do not need, because somebody else will look at that. That also you can do here. because in standard quantum theory we can always do local tomography, okay. But you know, so that is why it is possible. But in you know, if you go for example system of fermions or bosons, you cannot do the standard quantum. I mean there you cannot do this local tomography. So, you will have to do this by local tomography.
So, like if I ask some naive question, so if you give me a 2-qubit state and you tell me that this is your Hermitian operator and it will tell me its expectation value experiment. So, it's saying that any arbitrary Hermitian operator, you can just do LOCC and tell me the expectation.
See, LOCC in this sense that because I have to perform measurement of the Hermitian operator, right. So, I can choose a set of measurement of a set of observables on Alice's side, measurement of set of observables on Bob's side. It is not that measurement of any observable on Alice's side and measurement of any observable on Bob's side will be required in order to realize the measurement of this joint Hermitian operator. Some of them will require, but some of them will not be required, and that we will decide by classical communication. That we can always do. You know, this is simple. This is, you write some Hermitian operator in some basis, right? That I can always do, right. So, you write it in, let us say you know, something like j and k, like lambda j k s j for A tensor product s k for B, right, and these are real numbers. So, what I am saying is you perform measurement of these observables and measurement of these observables and then communicate, or somebody, some referee will see what are the things. Okay. So, that I can always do. So, basically what we have done here is to provide mostly interferometry based scheme to calculate determinant of A, calculate determinant of B, calculate determinant of C, and also calculate this thing. Okay. Or actually we have not calculated this, we have calculated determinant of gamma, that can also be done, you know, that is the most general covariant matrix, and that will give rise to, I mean, whether this condition is satisfied or not. So, I will tell you, I will provide you two schemes. The first scheme will actually be equivalent to tomography. That means, it will provide you the gamma matrix as well as the mean values. Okay. So, that means, for Gaussian state we know that is all, that will give you the state. So, this is equivalent to tomography, and I will try to convince you that, you know, this is actually this is what you should expect. Then what we will do, we will, so that is on single copies of the measurement done on single copies of the Gaussian state. Then what we did, we provided a scheme where you have 2 copies of the 2 mode Gaussian state, arbitrary, like in the case of 2 qubits 4 copies, 2 copies. So, there one can figure out this determinant of A by using interferometry method. Actually, you need to use swapping. Now, in practice for continuous variable system, realizing swapping is a bit challenging thing. Also, you can figure out determinant of B, and you can also figure out what is the determinant of gamma. We do not need this, actually this is fine. And then for determinant of C, it turns out that we had to do tomography, but only for C, not for entire gamma matrix. So, this is, you can say, partly tomography, partly other things, and that will give you you know, these values, and then thereby you can verify this thing, but you need 2 copies, and not only 2 copies, you need, I mean, to calculate this C part of the matrix, you need to use nonlinear processes like OPA. What is that called? Optical parametric amplifier, you know, that is what you need. So, so this is not tomography, but still we are not claiming that this is the best. So, that part is still missing.
So, then in some sense you tomograph the whole half state or full state to get the matrix.
Yes. So, you only tomogram tomograph the C part. So, you know here you have A, B, C, you only tomograph the C part, but for A you only find out determinant of A.
But it is done for in 2 copies. So
2 copies, yes, yes, yes. Yeah. I do not know, maybe if you use 4 copies perhaps you know you do not have to do the tomography of C also, I am not sure.
but so what about this other criteria, this nuance criteria?
Yeah. So, what I will do is I today maybe it will not be possible, next time I will discuss about one experimental work by this Bowen or somebody from Australia, you know Timothy Ralph and another group. So, they have done experiment back in 2008 or 9, I do not remember. So, there they have done experiment based on this Duan's criteria. Okay, maybe I will just go do fast. So, this is what we are planning to do, I mean detection of universal detection of entanglement in 2 mode Gaussian state, right. So, I will not go through all these details, this phase space description etcetera we already know. I do not have to do all this. Let me just go to the actual scheme, Wigner function etcetera also you know. Here there will be little bit problem with the you know the factors, like here in the case of you know I have taken this pi to the n because this is n mode thing. In our class we have not taken this should be not square root of, this should be square root of determinant of gamma, okay, and this pi to the n was not there in our discussion, but that is okay, that is so different people take different notation. Okay. Right. So, as we discussed so many times that for a 2 mode Gaussian state this gamma is your covariance matrix where A j k's are this, B j k's are this and C j k's are this. Okay. So, this is your R 1, R 2, R 3, R 4 are this x 1, P 1, x 2, P 2, right, and these are the reduced states, and both A and B are bona fide single mode covariance matrices, right, because that is what we know, and therefore, because these are, so they will also satisfy individually the uncertainty relation. So, here it is A plus iota by 2 sigma. So, capital omega, and capital omega is iota times sigma y. So, therefore, this is the relation they will have to satisfy. Okay. And you know that if rho 1 2 is a 2 mode Gaussian state, then rho 1 and rho 2 are also single mode Gaussian states. Okay. Right. Okay. Now, the separability issue. Okay. So, the separability issue is that we have already discussed that at the Wigner function level, this is not just for Gaussian state, any 2 mode state, Wigner function level partial transposition will take this Wigner function into this one. Okay. So, this is the relation, and the change corresponding change in the covariance matrix is this. So, you multiply the covariance matrix before and after by this diagonal one, okay, right. In fact, the condition for these n plus m mode Gaussian state. So, n mode is with Alice and m mode is with Bob. You know this condition, if gamma tilde is the covariance matrix of the partially transposed n plus m mode Gaussian state, then gamma tilde plus iota by 2 j, in this case j is your omega. Okay. So, this is what we have been talking about. So, here you see that the I mean the symplectic eigenvalues. Okay. So, what are the symplectic eigenvalues? So, basically you take your covariance matrix, whether it is single mode, 2 mode, n mode, whatever, you look at the Williamson's diagonal form. Okay. So, in the diagonal form of Williamson, whatever will appear, those are called the symplectic eigenvalues. Okay. These are not eigenvalues of the gamma matrix, because your symplectic transformation is not unitary transformation in general, right. So, but actually this gamma tilde, which are the symplectic eigenvalues of this gamma tilde. Gamma tilde is the covariance matrix of the partially transposed state. Okay. So, these are basically the eigenvalues of iota by 2 j in our case omega times gamma. Okay. So, this you can show that these are Hermitian matrices. This is a Hermitian matrix and therefore, you can talk about its eigenvalues. So, this condition of separability of n plus m mode Gaussian state is equivalent to saying that all the symplectic eigenvalues of gamma tilde, that means the eigenvalues of this Hermitian matrix must be greater than or equal to half. Okay. So, this we discussed I think for the 2 mode Gaussian state, but for general case this is the thing. Okay. Right. Okay. So, I said that this is the necessary and sufficient condition for a 2 mode Gaussian state to be separable, right. This is the local symplectic invariant terms. In principle, you can do it further simplification on this, and what you can show is that a 2 mode Gaussian state is separable if and only if, this is only for 2 mode Gaussian state, if and only if the minimum symplectic eigenvalue. So, how many symplectic eigenvalues you will have? Only 2, because if you think of the Williamson's form, you have these in the diagonal these nu 1 and nu 2 right, and in this case we call it so the minimum one of this tilde. So, tilde is so this tilde is at least, so the minimum symplectic eigenvalue of gamma tilde is at least half. So, in that case this is separable and this is a necessary sufficient condition. If you want I can tell you about it, but this is simple this is a paper which maybe you should look at it, this Pirandola's paper, Pirandola and other, this is a simplification of what Simon has done in his 2000 paper. Okay. So, this is more elaboration and all those things they have done. Nothing new is there, but a simplification of this paper. Yeah. Okay. And you can also figure out, so this is not there in that Pirandola's paper, but this is an earlier work by I think Adesso, Illuminati and others, where they have figured out the symplectic eigenvalues also of this gamma tilde. Gamma tilde, remember this is the partially transposed covariance matrix. So, they figured out that the minimum eigenvalue, minimum symplectic eigenvalue of this gamma tilde is of this form, square root of d, this is of course positive square root of d minus square root of d square minus 4 determinant of this, okay, right. And what is this d? D is this expression, determinant of A plus determinant of B minus 2 times determinant of C. So, this is the condition. So, therefore, you see the necessary and sufficient condition for separability of 2 mode Gaussian state is that this quantity should be greater than or equal to half, right, and that amounts to this d minus 4 times determinant of gamma is less than or equal to 1 by 4. Okay. So, this is equivalent condition. And you can also figure out that if I look at the negativity, what is negativity? Negativity is that you take the partial transposition of rho 1 2 and then figure out the negative eigenvalues and then take the magnitudes of those negative eigenvalues and add them, that will give rise to this negativity of rho 1 2. Okay. This is also entanglement monotone, it is not a good measure of entanglement, but that is okay. And this you can figure out that this is nothing but minus log of nu, this minimum symplectic eigenvalue, and this you can treat it as a kind of entanglement measure, not a good measure, but it is a kind of entanglement. Yeah, because the thing is that first of all, if it is PPT state, it cannot capture, okay, and then it I do not think it has this additivity property, etc. So, all those things are missing. It is not a faithful one. Yes, yes, it is calculable, but not a faithful one.
Measure has to be faithful, right, by definition.
Well, some measures are good, some measures are not that good. Okay, it is calculable, but not that good. Okay. Okay. And as I said, these are these local symplectic invariants of these two mode Gaussian state, the determinant A, determinant B, determinant C, and determinant of gamma. Oh, sorry. Okay. Now, let us talk. So, this I do not think you can see. This is so faint, I do not think you can see. Let me tell you. Okay. So, here one thing which you should keep it in mind, that so far when we discussed about the Simon's criteria about detection of entanglement in two mode Gaussian state, we have assumed that the local mean values, namely expectation value of x 1, expectation value of p 1, expectation value of x 2, expectation values of p 2, all are 0. Why? Because we said that look, if it is non-zero, we translate them, right, because that will amount to local unitary transformation and that will not change the entanglement. Okay. Now, in our case, we do not have that luxury. Why? Because we only know that the two mode state is a Gaussian state, we do not know anything more than that. So, we cannot assume that the local means are 0 or not. Okay. So, what we need to do is, and if you recall Simon's criteria, even this Duan's criteria also, they started with this assumption that the local means are 0, right. So, in order to use that criteria, we will have to take our system where the two mode Gaussian states have local mean value 0, right. So, for that we need to figure out what are those local mean values. Okay. That does not amount to tomography, we only need the local mean values, not everything. Okay.
So, assuming that the local mean is 0, the 0 mean Gaussian state, is that just for convenience to derive general mathematics?
It is just convenience,
Nothing physical about it.
Nothing physical about it. Only thing is, it tells you, it makes your life easier, nothing more than that. Okay. So, in order to figure out what are the local mean values, what is it that we have done? Unfortunately, we tried a lot, perhaps it can be made deeper, but somehow it does not work, I do not know why. So, let us say you have the kth single mode, which k can be 1 or 2, A and B, okay. And this is your local, I mean this is the classical mode, that means it is in a coherent state. Okay. This we call as AR, and then you put a phase phi. This is a 50-50 beam splitter, and then what you do here, the output modes we call it as A1 tilde, A2 tilde, and here you do the intensity measurements. That means, this A1 tilde dagger A1 tilde, A2 tilde dagger A2 tilde, intensity measurement. Okay. So, this is like homodyne. Okay. And then what you do, you look at the difference between these two intensities, that will give you idea about the average of AK, and because you have average of AK and AK dagger, you can figure out average of x1, I mean xk and pk also, right. So, that is what you will have to do, right.
So, if you went to the experiment, you will measure the
I1 and I2.
I1, I2, and you will look at the difference I2 minus I1 as a function of phase. You change the
Exactly. You choose different phases to figure out that, yes. And this is, I think, is experimentally it is easy to do, is not difficult. Okay. Yeah. So, okay. So, this is basically a schematic diagram for measurement setup to estimate all the elements of the covariance matrix associated with a single mode Gaussian state, not about the two mode one, okay, single mode Gaussian state. So, the kth mode of unknown Gaussian state and a reference state. So, this is your reference state, okay, which are prepared by the annihilation operator, this fine. They interfere at this 50-50 beam splitter, and a phase shifter is introduced at the reference mode here phi. The outputs of the beam splitters are represented by annihilation operators A1 tilde A2 tilde. The detectors generate the photocurrents I1 and I2, that is what we said, okay, which are proportional to the intensities at the output modes of K. And here what you do, you have two modes of the Gaussian state, okay, two mode Gaussian state. They meet at a 50-50 beam splitter first, and then you do the same thing. Here in this output mode, you have a reference oscillator AD and with phase shift pi 2 or phi 2, and here you have another reference mode this is I think AC with phase shift phi 1, and then you do this photocurrent measurement, okay, right. Yes. So, this is not just local, you will have to bring these two modes together here, okay, these two modes together. So, it is yes. So, you need to meet them in the beam splitter, at the beam splitter. So, you need to get hold of both the modes together.
So, the second set of B is basically to make the mean 0.
Yeah, well, not exactly, but yeah. So, if we look at the, I'll talk about that. What is it that we'll have to do? Okay. So, yeah, so this is same intensity measurement that we are doing. Okay. The next thing is, yeah. So, this is what. So, this is a well, you do not have to go through this lossless beam splitter, that is fine, So, this I think I prepared for some kits. So, I had to write all these things, okay. Okay. So, yeah. So, this is your measurement. So, first estimating the average values. Okay. So, measurement of this. So, these are called Stokes like operator, these intensity measurement. So, this is one Stokes like operator S1. Stokes, yeah, Stokes parameter, So, this is S1 phi, which is I2 tilde minus I1 tilde, the first A setup, right. You remember, this is what we have done, unfortunately, yeah, this one. So, I2 tilde minus I1 tilde, okay, right. Yeah. So, this is what we have done for phi, and this turns out to be this xk, I mean, this is the operator, of course, this is at the operator level. So, xk, this is for the kth mode, and this is xr phi. Okay. So, this is a rotated your reference mode. This is the position quadrature, and similarly for the momentum quadrature. Okay. So, this is the position, rotated position quadrature of the reference mode, and similarly for the momentum mode. Okay. And now you average over the many copies of the kth mode. So, what you get is this one, right. Okay. This is what you will get, because ultimately that this is acting on your kth system, this is on the reference system. So, this is what you will get, okay, right. And these values of these reference systems, this xr phi average value and pr phi for the reference system, this can be obtained by using, for example, a display squeeze thermal state of it. So, that one can always figure out, that is there in our paper also, but in principle one can do that. What are these? Because this is the reference state, this is up to my my choice, what is it that I am going to do, okay, the selection of phi and the reference state. So, in principle I can figure out these values. So, for example, you can, as I said, you can choose the reference state, initial reference state to be squeeze thermal state, single mode.
Depending on the reference state, if I choose some coherent state there,
Yes.
Can I get still the same effect?
You will not get same value,
Yeah,
you will
but
get
the
it.
same effect, so I have to choose phi in a different.
Yes, 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 yeah.
So that reference state is basically from experimental standpoint, it's like
Yes.
a local oscillator.
Local oscillator, yes.
So is there a reason why you prefer a displaced squeeze terminal over a coherent state, which is what people typically use as a local oscillator?
I think it will give you better robustness, I guess. Okay. Not more than that. Okay. I mean, this is also not difficult to prepare, but in principle one can do. Okay, good. So, by knowing this, so this you can experimentally figure out, right? This, because you have the state, 2 mode state, right? 2 mode Gaussian state, and on one mode you are doing this kth mode. So, you can figure out what is this value, because this is this one of these the Stokes operator. So, I can figure out that, okay, because I am doing intensity measurement, what else I can get. Okay. So, this I can figure out. Now, I know this side value, I know these local oscillator average values. What I need to figure out are these values. How will I do that? I change phi. I will have 2 equations, okay, and then I can figure out, because this will not change x k and p k, only these values will change. Okay, so, I can figure out that
So that's like solving a
pair of linear equations. Yes. So, this by knowing this experimentally and by using the prior knowledge of these local oscillator average values. So, I mentioned here phi is equal to 0 and phi is equal to pi by 2 will work, okay, right. We can find out the first order moments for the kth oscillator, and k can be 1 and 2, that is not a problem, okay, both of them. So, by this method you can figure out the average values, average mean values, okay, or the mean values of the yes. Next thing is the so this is about the mean values, but I need to also figure out the individual single mode covariance matrices, right, okay, single mode covariance matrix. So, now I calculate S1 square, okay. So, you can figure out S1 phi was this I2 minus I1. So, S1 square will be square of this at phi is equal to 0, and you can calculate things. This is simple algebra, it is nothing more here. I know what is the expression of S1 phi, the operator expression, and then from there you can at phi is equal to 0 you can figure out that this is the quantity. Okay. So, here you see square of this thing, quadrature squares, and similarly the product terms are there, right. So, this is at phi is equal to 0, at phi is equal to pi by 2 you can have this with this negative signs here. Okay. So, and in principle I can choose the reference state properly, so that I will have this thing. I mean, I am not sure whether these displaced squeeze thermal state will provide you this, but anyway one can do that thing, that is not a big deal. In principle one can choose that, but these are basically out of phase, one can do that. So, I have fixed these values, and also for display squeeze thermal state one can find out display values, not only for display squeeze thermal state, any classical state you can figure out, and therefore, one can figure out square of this, right, because this is 2 equations for phi 0 and phi pi by 2. So, you can figure out these quantities.
Oh, the procedure is still the same to calculate the first and the second movement. Basically, change the phase, get 2 pairs of equations. Yeah, system
Yes.
of 2 equations, and so.
Yes, yes, for the single mode, okay, right. And now, this also you will have to calculate, because this is for the single mode, the cross term is there. Okay. So, you can calculate this thing. So, here I have chosen phi is equal to pi by 4 just for other things, and inserting this equation, the values of, you can insert these values and this value also, you can find out this x k p k plus p k x k. Okay. So, what is it that we have done? We have figured out what is the single mode covariance matrix, entire thing, I mean as well as the local mean values, right. So, if you want, you have this A C C transpose B, you know A and B now, okay. A and B completely. Yes, using just the interferometry, nothing more. Now, the question is how to figure out elements of C. So, we have figured out elements of A and B, elements of C. Okay. So, so now you need this second figure. So, because you need these two beams. Okay. So far we have used only the first figure, figure A. So, you need the second figure, figure B. So, there you have the intensity difference at the two output modes of the beam splitter, which is basically this. The same thing, you know what we have done for single mode, second figure we have done for two modes. So, you have 4 intensities, I think I 3, I 4, I 5, I 6. So, you can look at S 1 phi 1, which is this intensity difference, and this will be of this form. Similarly, intensity difference at the two output modes of beam splitter 3, you know. So, we have used beam splitter 2 and 3. Okay. First one where the two modes of the Gaussian system or two mode system meets, and then they go to this beam splitter 2 and beam splitter 3, 50-50. So, this is what you will get. These are usual thing, you know, nothing special about it, right. So, one more. So, this is again Stokes measurement, okay. S 1 phi 1 and S 1 phi 2, again this Stokes operator. So, another Stokes operator measurement that we need to figure out, we need to perform Stokes like measurement. So, joint measurement on the two output modes of the beam splitter 2, okay, and 3. Okay. So, this is the joint measurement, and this joint measurement. So, this is on A 3 and A 6. So, maybe let me go back to this. Yes. So, yeah, sorry, I do not think you can look at it. This is A 3, A 4 for the beam splitter 2, and this is A 5 and A 6 for beam splitter 3. So, you will have to do joint measurement on A 3 and A 6. So, which involves I 3 and I 6. Okay. Is that no? Yeah. So, this you will have to do measurement of the Stokes operator. Okay. And what you need to do is to measure this anti-coincidence of the photons to be detected by using photon number resolving detectors at these two output modes. Okay. So, you will have to do this anti-coincidence. Okay. So, if you do all this, you can figure out C matrix also, entries of the C matrix. Okay. So, here also you see that everything is linear optics, right. I mean, if you assume that your local oscillator is prepared in some specific state, right. Okay. So, once you know A, once you know B, once you know C, you know gamma, and therefore, you can figure out determinant of gamma, you can figure out this quantity, you can figure out whether this is satisfied or not. So, everything can be done, but there is a problem. Problem is this amounts to tomography, because for two mode Gaussian state, if you know gamma and if you know the mean values of the individual modes, you know the entire state, right. So, this amounts to tomography, but you know what is big deal. I mean, if you do tomograms, of course, you will get to know the state, and therefore, its entanglement, everything you know. So, what is big deal? In fact, this has to be the case. So, for finite dimensional systems, bipartite system, it is known that detecting entanglement universally, because we are aiming at universal entanglement detection, not for specific state. of course, for the Gaussian state, 2 mode Gaussian state. So, detect for finite dimensional system, detecting entanglement universally for 2 more, I mean for bipartite system, finite dimensional system, using a single copy of this state. See, here also we have used single copy. So, this would amount to quantum state tomography for a finite dimensional system, and this is the work by Carmeli et al, where they have shown that whenever you use single copy of your state for bipartite finite dimensional system state for is detection of entanglement, this will amount to state tomography. And in our scheme we are doing the same thing, we are using single copy of 2 mode Gaussian state, it is not finite dimensional, infinite dimensional, but it amounts to state tomography. Okay. So, of course, one cannot say that this is the rigorous proof that if you want to do entanglement detection for 2 mode Gaussian state using single copy, it will amount to state tomography. Our scheme is such that it will amount to state tomography. Okay. So, question is, can you improve it so that it will detect entanglement, but not the state itself. So, it will not amount to state tomography. So, that is the question, and that has some answer. It may not be the best answer, but this is the answer. So, it is known that for a 2 mode Gaussian state rho 1 2, again this pi square may or may not be there, because we are using a different scaling. So, if I take trace rho square for a mixed state, of course, this is not 1, this is less than 1. If I take trace rho square, this will amount to calculating this integral. So, you take the Wigner function square and then average it out, that is the trace of rho square, okay, and that will amount to 1 by square root of determinant of gamma covariance matrix. Okay. So, what does it mean? It means that if I know this quantity by measurement, then I will know determinant of gamma. Okay. Similarly, if I calculate trace of rho 1 square is reduced density matrix of mode 1, trace of rho 1 square, rho 1 is that, then it will amount to 1 by determinant of A. So, therefore, if I know this, I will know determinant of A. Similarly, for determinant of B. Okay. And what is this trace of rho 1 square? So, you take 2 copies of rho 1, I have called it 1 prime, but the states are same, 2 copies of rho 1, and then you measure the swap operator on these 2 modes S1 1 prime swap operator, okay, right, 1 plus 1 mode swap operator. Then what you will get is trace of rho 1 square. So, therefore, if you can provide me 2 copies of the 2 mode Gaussian state, therefore, 2 copies of the reduced states also, and I perform measurement of these 2 mode swap 1 plus 1 mode swap operator on that 2 copies, I will get trace of rho 1 square. Now, question is, how will you actually realize measurement of the swap operator? That is a big question, but in principle one can do. There are some proposals for realizing swap operator for infinite dimensional systems also. Similarly, I can figure out what is trace of rho 2 square. Same thing, I perform measurement of this swap operator S2 2 prime on rho 2 copies of rho 2.
So, these 2 copies of rho 1 basically mean that mode is fed to the swap operator.
Yes. So, you prepare these 2 mode Gaussian state 2 copies, this is with Alice, this is with Bob, this is with Alice, this is with Bob. The 2 modes of Alice you fed to this swap operator, similarly these 2 modes of Bob, okay, right. And this one is rho 1 2 square, this is basically 2 plus 2 mode swap operator, is 1 1 prime 2 2 prime, and this is 2 copies of rho 1 2. So, that is why I said you need 2 copies of the state. Okay. So, basically you need performance of measurement of these 1 plus 1 mode swap operator on Alice's 2 modes, 1 plus 1 mode swap operator on Bob's 2 modes, and these 2 plus 2 mode swap operators on Alice and Bob together. Okay. So, this will provide you determinant of A, determinant of B, determinant of gamma. So, you do not need tomography. Okay. Now, how will you do that? Yes. So, so now the question is finding out determinant of C. So, as I said, we are still unable to figure out determinant of C without doing tomography of C. Okay. Maybe there is a clever way of doing that, but still we are not able to do. Okay. Now, what do you do? So, this is your 2 copies of the 2 mode Gaussian state rho 1 2, one with Alice, one with Bob. I mean this is one copy, this is another copy, one with Alice, one with Bob. So, this is the modes of Alice, which I call A11 and A12. They are going to this OPA, I mean this is optical parametric amplifier, okay, and this is a nonlinear gadget, and then you pump it with some laser, right, and depending upon the pump frequency etc., you can figure out what will be these output modes, okay, right. Similarly here, and you will have to do it simultaneously. This is in Bob's place. So, this pump OPA and this pump will give rise to these parameters mu 1 nu 1, and here it is mu 2 nu 2. Okay. So, and then on these modes you put photodetectors, okay, right. So, the details are there in our paper. So, fine. So, you can do so you can, as I said, you can figure out the mean values as earlier using the interferometer. So, that is not an issue, and then you can translate your state to make them 0, right. That is also possible, that is because the amount of translation will depend upon the values, mean values. So, you can translate them to make them 0, and now Alice and Bob share 2 copies of these 2 mode Gaussian state, each having mean values 0, local mean values. And then they say, as I said, you send them to this optical parametric amplifier, okay, with parameters mu 1 nu 1 and mu 2 nu 2, and they will output these fields. On Alice's side A 3 with mu 1 A 1 plus nu 1 A 1, this is A 1 2 and A 1 1 dagger, and similarly A 4 on Alice's side, okay, and on Bob's side also you will have 2 oscillate field modes. Okay. So, this is how the OPA works. So, you have the pump which will figure out what will be this mu 1 nu 1 and mu 2 nu 2, and this will give rise to the new fields. Okay. So, yeah, so this is basically mu 1 is cos hyperbolic g 1 and mu 1, all these things, and these are the parameters g and phi, parametrical strains depending upon the intensity of the pump beam, nonlinearity of the OPS crystal, and phase of the pump beam. So, that is how it works. Okay. So, you can now measure the Stokes like operator. This is the Stokes like operator, do you measure? It is like a beam splitter kind of thing. Okay. This kind of operators you measure, and you can find out its average values. These are the constants, and then you can figure out the average values. Okay. And by performing measurement you can find out these average values directly. This is how our experiment works. The Stokes like operators you can measure directly in experiment. Okay. So, this will provide you basically the matrix element C, because these are the quantities, these average values of P1, P2, x1, x2, then x1, P2, etc. This will provide you the matrix elements of C. Okay. And once you get that, then so what is it that you have seen? So, therefore, you have determinant of A, determinant of B, determinant of gamma, and the C matrix itself. So, how many measurements you have done? 3 swap operators to figure out determinant A, determinant B, determinant gamma. Also, the measurements of the 4 Stokes like operator that I mentioned just in the previous slide for determining C, and measurements of the 2 Stokes like operator S1 phi 0 and S1 phi pi by 2 to know the local mean values. Okay. And this is all. This will provide you the not the entire covariance matrix, but it can tell you whether this condition is satisfied or not, the Simon's condition. Okay. And so, this scheme requires in total 9 measurements in order to detect entanglement in an arbitrary 2 mode Gaussian state. And as I said, we do not know whether this is optimal or not. It may happen that without even figuring out the matrix C, you can figure out its determinant of C, that is may be possible, but we still do not have the solution for that. But this is better than tomography, that I can share. Okay. Right. So, this is the scheme for detecting entanglement in 2 mode Gaussian state, arbitrary 2 mode Gaussian state.
It could be pure or mixed.
Anything, it could be pure, it could be mixed, anything. It may not be optimal, that is okay. Yeah. And we have also done some robustness analysis, it is not. So, well, the question is, can we make it a measurement device independent scheme? Possibly not, but we can figure out how much error we can allow. So, that we have done, we will have to basically we will have to add them here. So, like detection error, beam splitter error, these, that, how much error it is allowed, that can be done. Okay. Yeah. So, this works for mixed state, pure state, everything.
So, where has this work been published?
Not yet, because we are doing this robustness analysis.
Oh, okay.
So, this is almost done. Once it is done, then we will send it for publication. Yeah. Yeah, this is a work which has been pending for more than 2 years. Yeah, because people are traveling here and there. So, this is the problem. Yeah. So, next day I will try to discuss about the other work, this Timothy Ralph's work about which is based upon this Duan's criteria.